Hello everyone, I am presenting on behalf of my team, Submersivity XR Guided Garbage Detection with an RC submarine for Peter Street Basin cleanup, developed by Chris McGill, uh, Michael Herrera Villela, Chan Park, Daniel Bros, Alexander Vico, that's me, and Professor Steve Mann at the University of Toronto. The purpose of submersivity is to close the loop between underwater perception and human action. An RC submarine captures underwater imagery. An object detection model identifies garbage. A mapping pipeline places detections in basin coordinates, and an XR display guides a swimmer toward the detected debris. Peter Street Basin is an outdoor safety pool connected to Lake Ontario's inner harbor. It is approximately 60 meters by 30 meters. Debris can accumulate below the surface while remaining invisible to people observing from above. Human inspection alone is inefficient at this scale. A swimmer or diver may be able to see nearby objects but cannot easily survey the entire basin. Remember the location of each item and then navigate back to those items without spatial support. There is also a gap between common underwater robotics tasks and cleanup. Much research focuses on reconstructing an environment or localizing a vehicle. Those are important capabilities, but cleanup requires an additional step, converting a detection into guidance that a person can actually follow. Our opportunity is therefore an end-to-end system that detects debris, places it on a map, and guides a human cleanup volunteer in real time. The emphasis is not on replacing the person, it is on giving the person actionable spatial information. The full system is organized as a five-stage pipeline. First, we designed and built the RC submarine as the underwater sensing platform. Second, the submarine acquires underwater frames and transmits them to a host server. Third, a fine-tuned YOLO V8 model detects garbage in those frames. The training process uses more than 12,000 images and treats garbage as one broad class. Fourth, the system localizes detections relative to a three-dimensional model of Peter Street Basin. ColdMap provides the reconstructed geometry and camera poses, while ARUCO markers connect that reconstruction to known real-world basin coordinates. Fifth, the resulting target location is sent to XR swimming goggles. This user actually sees a direction, a distance, and a map rather than a raw bounding box. The important contribution is the connection among these stages. Detection alone tells us that debris appears in an image. This pipeline is designed to tell a person where to go retrieve it. The underwater sensing platform is based on the open source ESP Dive design and XIAO ESP32S3 Sense module. The camera can capture up to QXGA resolution or 2048 by 1536 pixels. For real-time streaming, the operational setting is 800 by 600 at approximately 5 frames per second. This practical trade-off between image detail, bandwidth, and responsiveness. For buoyancy control, the vehicle uses two piston ballast tanks driven by geared motors. These allow adjustment toward natural buoyancy. A single reel thruster provides propulsion and steering, and the system is designed for operation to a maximum depth of 5 meters. Because ordinary Wi-Fi does not propagate effectively through water, the RF connection is moved to the surface. A 5-meter coaxial cable connects the submerged vehicle to a surface buoy, keeping the wireless link above water while the hull remains below. Battery life is approximately 30 minutes per charge, and wireless and magnetic charging supports repeated operation. These constraints define the present survey duration and operating depth. Now, for the perception model, we've found that task definition was just as important as model choice, more or less. The combined datasets contains 12,177 images drawn from the TACO terrestrial litter dataset, the trash can underwater debris dataset, and underwater images collected by the team. All annotations were unified into a single class called garbage. The model is YOLO V8 small, initialized from cocoa weights, trained using 640 by 640 inputs, batch size 8, mosaic augmentation, random flipping, HSV perturbation, and random erasing. The table shows the progression of fine multi-grade, multi-class model trained on approximately 1,500 taco images, reached an MAP50 of 0.27 and a precision of 0.37, converting the same taco data to a single garbage class increased MAP50 to 0.49 and precision to 0.71, with a combined 12,177 image single class dataset. Both MAP50 and precision reached 0.92 in the combined validation set. This was a great result that reflected the actual cleanup objective. A volunteer does not necessarily need to know whether an object is a specific packaging subtype. They just need to know that it's garbage. The first question is whether it is garbage, and then that should be investigated. And then collapsing the taxonomy therefore reduces unnecessary classification complexity and improves practical detection performance. Detection becomes useful only when it is connected to a physical space. To construct the basin map, a 3-camera GoPro rig was walked around the perimeter of Peters Street Basin, registered around 796 of the 823 above water frames, which is a 96.7% registration rate. However, a cold map reconstruction begins in its own arbitrary coordinate system. To relate it to the actual basin, we used ARUCO 4x4 markers with 19.5 centimeters slides, placed at known locations at the basin wall. Three known, their known three-dimensional positions provide the transformation into a basin-aligned real-world frame. Each submarine detection can then be projected into basin coordinates using the relevant camera pose. Over time, this produces a spatial map of detection events. The map on the right shows this visualization. The swimmer then receives guidance through Vuzix Smart Swim goggles. These are monocular, full color Android-based goggles designed to preserve the natural field of view while adding a compact heads-up display. So first, a compass-like arrow points toward the nearest target. Second, a range readout reports the estimated distance in meters. And then third, a miniaturized map of Peters Street Basin shows the submarine position. The principal detection result is precision of 92.1% and an MAP50 of 0.921, as we discussed before, for the combined single-class YOLO V8 model. Qualitatively, the model can detect packaging and plastic debris under partial occlusion, more or less, so low contrast and underwater color shift. The examples on the right show detections in these visually difficult scenes, including a small object at a distance. So, in one preliminary survey run, the system actually recorded 130 garbage detection events. It is important to interpret this number correctly, as these are frame level events, not yet 130 unique physical objects. The result therefore demonstrates that the integrated detection and mapping pipeline operates in the field, and while also identifying the need for multi-frame association before event counts can be treated as object counts. The main insight is that underwater cleanup assistance benefits from combining perception and guidance rather than treating object detection as an isolated back-end task. This is really helpful for the field of computer vision as well. So combining more than one piece of information actually helps the system with more context. And this isn't even for LLMs. This is just for computer vision, right? The single class strategy was particularly important because of a fine-grained taxonomy reduced practical performance for this use case. And so the physical platform introduces further limits. The ESP dive is rated to a maximum depth of 5 meters. Battery life is only about 30 minutes, and the dome port only partially corrects refraction. So these are sort of issues that still, with these sort of challenges, we are able to produce this great result, which is helpful for computer vision, we think. In conclusion, submersivity closes the loop from underwater detection to human-guided retrieval. The integrated system combines an RC submarine, a single-class YOLO V8 detector, Map, and ARUCO mapping, and an XOR heads-up display for basin scale cleanup assistance. The validated component includes 92.1% detection precision of the 12,177 image combined datasets, registration of 796 out of 823 coal map frames, and XOR target updates at 5 to 10 Hz. Most importantly, the human receives actionable cues rather than raw computer vision output. This makes the cleanup process more interactive, intuitive, and spatially aware. Next steps are clear. We want multi-frame association, such as DB scan clustering, and eventually we'll merge repeated detections into confirmed physical debris locations. The broader takeaway is that underwater robotics can support people not only by seeing beneath the surface, but by translating what the robot sees into guidance that a person can immediately use. Thank you.